we've picked out all the individual pieces of our program, and now we need to put them all back together. So this stage is also known as parsing, and it uses the tokens from the last stage to form meaningful structures. And this is completely based off of the defined grammar, which is why grammar is so important. This stage in grammar, they go hand in hand. You can't have the syntactical analysis without a properly defined grammar. And so what's the final result? I said we form meaningful structures, and we can actually quantify those as abstract syntax trees, or ASTs. And we'll break down what that means in a bit. But for example, if we have the tokens 3, the plus sign, and 2, our meaningful structure might be the add operation. And we can say there's an add operation between the number 3 and 2, right? So it's not the same thing. We're taking these apart and we're constructing a structure, but it's going to hold that meaning, right? We know we want to add these two numbers together. So that's what we're representing here in a data structure. And this will actually represent the relationship of the input. So what does this look like? Well, firstly, this is what an AST looks like in a kind of a tree format. But let's start from the top here. So we have our input, 22 plus 7, nice and simple. Then we can break it down into tokens. So we can have a number token, 22, operator token, plus sign, number token. I'm just realizing we didn't actually pause before. So we can do an extra long Q&A after. Number, which is another 7. And then here's our grammar for our calculator right now. So this isn't going to be your full calculator. As you can see here, this is just going to be one number, operator, another number, right? And so the only number, or the only operator we find here, is a plus sign. So basically any number plus any other number. And here we can see our two syntax formed together. So we had digit, which was 0 to 9. And then we have this plus sign. If you remember back, what that means is that we can have a bigger number than just one digit, right? So we can have 1, we can have 10, we can have 127, we can keep going after that part. So once that's all said and done, this is just kind of another way of showing this add operation. We can represent it like this. So we have the add operation. It has 2 children. So that's what they're kind of called. We have number 22 and we have number 7. And that's going to be a hierarchical kind of representation there. And so what is an AST? Well, that's what we just saw. Again, abstract syntax tree. It's going to be hierarchical. That word is brutal, huh? But it's basically going to show some sort of hierarchy here. So we can see that number 7 is lower than the add operation because it belongs to it. We'll see a better example of that after. Why is it abstract? Well, it omits redundant syntax. And so if you think about, we'll have an example further on, but if you think about like a piece of code, for example, dress it up however you want between different programming languages, right? Syntax, you're going to have, let's say a variable assignment in one language, a variable assignment in the other language. They might look completely different, but at the end of the day, what's the meaning behind that? Well, we're just trying to assign a variable. So let's ignore all the syntax and just capture the meaningful structure. And that's what AST is. That's why it's abstract, because we can't objectively say that this operation belongs to Python or this operation belongs to C++. It's just the or it's just the assign operator altogether. And just to kind of recap, what's a tree? Well, tree is a data structure with leaves and roots used to represent hierarchies, right? So this is the root of the tree. These are the children or the leaves. And there we go. So this is what our calculator grammar actually is going to look like. So we're going to have an expression, term, factor, and number. I know this looks like a lot, but let's break it down just like we did before. Before I do that, okay, before I break down the calculator grammar, does anyone have any questions? You can raise your hand and you can ask them, or you can type them in the QA. This can be, any part of the presentation at the start, the end, where we are now. Is anyone confused? Anyone need further clarification? Do we have the Q&A channel going? Are we all good? We got one question. Connor, do you want to unmute them?
It should work now. Now try on your side.
Oh, I'm unmuting them?
Yep.
I thought you were Mr. Unmute. Sorry, could you raise your hand?
Sorry,
Okay.
can you raise your hand again, please?
Maybe they don't have a question anymore. You don't have a question anymore? We good? Okay, there we go. What's happening?
Go ahead and ask your question. We've now made it so you can go ahead and unmute.
We also have a general chat if you just want to drop it in the chat. Whatever you feel the most comfortable with.
It looks like, okay, they post the question now. So the question for you is, why should we use an AST and why not RPN instead?
What's our RPM?
RPN, reverse polish notation.
First polish notation. Oh, I see. Okay.
Why use an AST instead of reverse polish notation?
Yeah. Full disclaimer. I'm familiar with reverse polish notation, but basically it's just a weird way to format, I guess, language so that you can use a stack to calculate it that way. Yeah, that's a valid point. For this specific example, I'm not saying that calculators, you need to do them this way. It could be, and probably is, extremely overkill to do a full language pipeline for calculator grammar. Unless it's an advanced calculator like you might see on Desmos with variables and stuff like that, it's probably going to be overkill. Now, why is it important? Well, as we've assessed, there's multiple different forms of language processing, whether it be, the programming language, all the AI features that we're using these days, like, ChatGPT uses these, your spell check in your computer, like all of these technologies use it. So it's not a matter of, hey, let's build a calculator. This is the way we're going to do it. It's deeper than that. We're just trying to put it in a more digestible way so that you can understand the process, because this is one way to have a calculator with more advanced features. So there are multiple ways. Reverse polish notation could be a clever way to do it as well. For this, we're just trying to show the example of how does language processing actually look like, and what are the steps of doing it. And so this is one approach of making a calculator, but after this, it will give you the fundamentals if you wanted to do something like a regular expression engine, or if you wanted to play around with programming languages, or whatever the case may be. So yeah, that's kind of why there's multiple ways to do it, but it's more of a fundamental of understanding, just kind of a way to be able to learn about it with, I guess, relative ease, without having to describe all the complexities of every other different system.
And one more question, maybe you can demo it. Maybe it would be good in the live demo for this one.
Okay.
From Brian, is how are you getting the tokens from the tokens to the AST or corresponding operations? Not sure. Maybe if we can fit that during the live demo, or whether you can explain in theory now.
How to get them from, like, how to actually use the tokens? I might be. Where did you see the question?
It's in published on the Q&A.
Okay, how do we go from getting the tokens to the AST? Okay, yeah, so that's a great question. I guess we can roll back here for a second. Okay, so when you have a grammar like this, that's why I said they're kind of hand in hand. Your tokens may be like these words here: the, dog, pets, blah, 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 blah. So you have a bank of tokens to pull from. And it's very much just like this. Well, then we can use those tokens in a little bit of our own logic and start fitting pieces together programmatically. So we can say, okay, I'm trying to construct a verb phrase. So let's say my verb phrase is an AST, and it's gonna hold both the verb and the noun phrase. And of course, the noun phrase again is gonna hold an article and a noun. And so what you'll actually end up getting is like a nested tree. Oops. Right. So you can see here's a calculator with a little bit more complexity. You'll get a nested tree like that. So that's kind of what we're going to be doing here by forming these more complex sentences out of the AST. And it's exactly the same. So I want to construct a verb phrase. Well, I have my bank of tokens, and I want to pull the first one. I want it to be a verb token. Okay. I want to pull a verb token. All right. So I can see, okay, likes. Okay, that's a verb token. Great. Let's use that first. Okay, so we have that. Now let's move on to the second part of our section. So now I need to, using the grammar, I need to construct a noun phrase. Okay, well, what does a noun phrase have? Well, it needs an article and noun. Great. Is my next token an article? If it is, then we can keep constructing the sentence. If it's not, then I can say there's an error there, right? So if you gave me, and this is a list, right? So if, where is it? Okay. So if we have tokens here, so they're going to be operating in a list like that. And when we're assembling, and again, I won't go into too much detail here because we'll actually cover it very fully when we do the practical demo. But we have a list like this, and basically we're just taking items off the top. So they've been delivered it to like this. They've been delivered it to us like this, right? So the first element there is going to be a number, and then the second one's an operator. We can see it reads from left to right as we go down the list. So we're taking the top thing and we're checking if it fits in properly, right? So if you were to give me a sentence, let's take one of the sentences that was here, and I can show you how this actually works. So the dog pets the boy. So that's the sentence. Imagine that in a list. And so we're going to take the first thing from that, the. Okay, great. So we have a sentence here, the. Okay, well, it needs to be a noun phrase. What's a noun phrase? Is it an article? Is the an article? Is it an article token? Yes, it is. Okay, that's valid. Let's get rid of that. And let's move on. Okay, next word is dog. So we're going to have a noun. We're going to have a noun token with the value dog. Okay, let's look here. We need a noun. Great. Valid again. Move on. Okay, what's the next thing that we have? Pets. Cool. We need a verb phrase. Is pets a verb token? It is. Great. We can move on. And as we're building through this grammar, we can start extracting things. We can extract, dog. We can extract, the meaningful information from that. And, if we have, for example, we say a sentence needs to end in a period, we can discard that because it's not important. And we can just keep pulling from our list that we're given, and we can assemble all of the most important things, and then we can put it all together nice and elegantly at the end. So that's the way that grammar fits in. We're going, one by one, dissecting what we've been given, dissecting the token list, and slowly, proving that it is valid, because otherwise we'd like to tell the user that their sentence is not valid or their program is not valid or whatever, right? And then number two, we're dissecting that important information so that we're able to construct something more meaningful. Does that kind of make sense? I mean, again, we're going to go into a lot of detail when we actually do the implementation, but that's sort of how that relationship works there. Just a simple, sounds good. Anything? Any other questions? All right, sweet. All right, I don't think there's any more questions, so we'll move on here.
We've got one question.
One more question.
From Ishmak, if you have two valid tokens which are similar but perform different operations, how do you actually differentiate? For example, added versus adder.
Okay, so this is where we start looking into the practicals, because everything we cover on the theoretical is not going to obviously matter in the practical. Like obviously there's going to be a large part of it that matters, but stuff like what you just asked, right? The glass and the glasses, or added versus adder, stuff like that. So added and adder, I guess, are pretty simple, and I'll tell you why. It's because they're the same length. So is adder, is that a valid word? Are we assuming that's a valid word? I don't know if that's a valid word. Connor, Mr. Linguist. Anyone?
Sorry, is adder a word? Is that what you're asking?
Yeah, is it a word?
Like,
I don't think it's a
I
word.
don't believe so.
Okay,
Like when
well,
I've done
we can take the example either way.
something. Yeah.
So adder, for example, let's say it is a valid word, which I don't think it is. Let's say it is a valid word. That becomes a little bit more complicated, right? Because if it wasn't a valid word, we could just simply say, okay, well, added is a valid word, so let's just take that instead, right? Adder, I don't think it's a real word. Let's say it's not a real word, or sorry, let's say it is a real word though. So we're kind of at the situation where, you know, we're trying to differentiate. Maybe even like as simple as we have different operators. How do we differentiate between the two of them? And that's where it kind of comes down to the value, right? So we talked about the two different parts of our component, or we talked about the two different types of information that we're storing in our tokens. Somewhere. Here we go. So contextual information is kind of like your surface level overview, right? So like I have two words or I have two nouns. That doesn't tell me anything. That can tell me kind of the first thing. Hey, I want this to be a noun. But you know, in the grammar we showed here, this is not specific at all. The part of this is that it could be any noun, it could be any verb, it could be, well, obviously in the list, but it could be anything. When we look at our calculator grammar, although, you'll find that there's actually specific values that we need. So when we're looking through this, again, there's going to be a little bit of like difference between implementing it and like expressing it in grammar, right? We're not definitively saying we need a symbol here. We could extract that a little bit more, but it's just not as necessary in this one. We're saying that we can either have a plus symbol or a minus symbol. So in the actual implementation of this program, we could kind of at a surface level say, you know, if it's not an operator, we don't want it. And that could be a surface level, you know, identification, but I don't think it would be particularly helpful. You'd want to say, okay, well, you know, is it an operator? Great. If it is an operator, is the value a plus symbol? You know, if it is an operator, is the value a divide symbol? Right? So through more contextual information, because what you'll see is that every token is actually just its own data structure in the actual program. So we can provide, as a developer, more contextual information to help us make those differentiations, right? We don't want any ambiguity. And that's kind of what we're trying to, you know, avoid. So if you're running into that, your grammar is not configured correctly, or your program could be reworked in a better way. So that's where I'll keep it for right now. It'll make more sense actually when we start going into it. And then again, like that glass and glasses thing is going to be a whole different discussion. But at a surface level, we have, you know, multiple parts to identify each token for that specific reason, so that we're not getting all jumbled up. Again, you said like kind of similar, but we're sticking to full, you know, objectivity, right? There's no kind of in a computer. It's either one or the other. It either is or is not. And so that's what we're going to rely on in these systems. Okay, that'll be it for now. If you have more questions, drop them in the chat and someone will answer them. That's not me. Just want to keep this presentation moving. So calculator grammar, here we go. So let's break this down a little bit. So number, again, we've covered this, 0 to 9, one or more digits. Okay, factor, what's a factor? Well, this is where we kind of get our group syntax. A factor can either be a number, or it can be an expression with, you know, braces around them, parentheses around them. Well, what is an expression? Well, that's up there, but let's first look at term. What's a term? It's a factor. Or, and so there's multiple brackets here, but any actual bracket symbol is going to be in these these, you know, quotation marks. It can be a star, or it can be a divide symbol and then another factor. Again, look at this star here. So this means that this entire block is completely optional, or we can chain together as many expressions as we want, right? So we're not going to spend too much time on this, but again, term, plus symbol, minus symbol, term. Now you might be wondering, why do we differentiate between, you know, term and factor and these different operators? And this is the way that this is designed, is that if you follow this formula, you will have order precedence at the end. Everything will sort itself out, right? So we'll just stay with that. Last stage, semantic analysis. Now this isn't always used, but it's used in a lot of, you know, meaningful programs. this stage is really, we've constructed everything. Let's just make sure it makes sense, because we can construct an operation and it just can fail logically. For example, with our grammar, we can construct a divide operation with 2 and 0. But I mean, logically, that is incorrect because we know that we cannot divide by 0, right? So these are kind of the edge cases that we're going to be looking for in the semantic analysis. And so, so this is going to be evaluating over the actual AST and making sure that everything looks okay. And then again here, sorry, another example. If we have an integer, which is a whole number, and we give it the value hello in these brackets, right? Or sorry, these parentheses or quotation marks, hello is not a valid integer. So again, that's another logic fail there. Oops. All right, and then the final stage is meaningful action. So this kind of really just depends on what you want to do. Once you get past the AST and you know that it's correct through the semantic analysis, it really depends on what you're trying to do next. So those are the fundamental 3 steps. Let's just kind of go over maybe, if you want to develop a programming language, there's 2 ways to go about it. If you're doing a compiled programming language, then you'll lower that down to an IR, which is intermediate representation. Or if you're using an interpreted language, you'll just straight up execute that instruction. If you're doing a calculator like we are, you'll just evaluate the result, right? Once we build up that AST, we'll have to find out what the number is after. If you're doing a spell check, you'll do a lexicon lookup, make sure that we can, maybe auto complete that or check if it's spelled correctly. And then if we're using a regex engine, regular language engine, then we'll be building an NFA or a non-deterministic finite autonoma. And so here are some real world examples of what this actually looks like. So we have, a C-like language. So int x equals 10. So we're taking an integer with the name 10 and we're giving it the value 10. So what are our tokens going to look like? Well, we're going to have a keyword int. We're going to have an identifier x. We're going to have a symbol, the equal sign. We're going to have a number 10. And then we're going to have the symbol, which is the, semicolon. And look like? Well, we're going to have the assignment operation with a type, a name, and a value. Those are the 3 things that matters. And remember how I said that it omits, optional or not optional syntax, but insignificant syntax. Well, the assign operation doesn't need the semicolon or the equal sign there, right? Let's extract those tokens that don't really add to the the instructions or like the meaning of it, and we can just break it down into this format, simple and easy. That's why it's abstract. Assignment, it's type the name of the value. Okay. And then from there, we might break that down to an IR, which will look something like this. Now, we're definitely not going to dive into this, but just to kind of show you the full pipeline, we're going from a nice, easy to understand expression to tokens to the AST, which gets lowered down to this, and then that'll be turned into machine code, which will be run. Let's look at our calculator now, because this is actually what we're going to be building. So we have 3 plus 5 times 2. Again, all of our tokens there, nice and simple, builds into this, right? And now look, we have our order of operations here. We have our number 3, and as we dive down, we have to do this multiplication first before we can add it back up. So in that, it's constructed so that order of precedence actually matters, which is super, super neat. And so yeah, that's kind of the theoretical section. That gives us all the tools that we need to actually build something. And so we're going to do questions in just a second, but what is the practical section going to look like before, if anyone's interested? I have done the full code already. And then what I did is I made kind of a template. So I have all of the frameworks set up, right? All the functions are there. All of the files are all linked together, everything like that. It's in Python. But I just left all of the function bodies empty so that we can go through them as a group and actually see what the development looks like. And I've added comments and everything like that. So if you're new to development, you could just follow along. But if if you've been coding for a while, it's still not going to bog you down with all the template stuff as well. So that's what I'll say, and we'll probably start that in, I don't know, whenever anyone has any more questions. So anyone have any questions? Final questions for the theoretical section? You can raise your hand, you can post the question. About a moment here.
Last go. Let me check.
Doesn't look like we got anything
Nope.
going here. That's fine.
Nothing
Okay.
on there. Why
That's good.
don't you put like your code snippet in a discussion post? So if you put it in, you just hit the code snippet, paste in there, and then they can copy and paste right into their IDE.
Yeah. So I have it on a GitHub branch, which people can download here. I'll post it in chat. So yeah, so I already put it on my GitHub here, so you guys can just download it and you'll have all the code already there.
And
Okay,
we
I've just
can
posted
look
that.
at sending the slides out after the session.
Yeah, we'll send the slides out too, so you guys can have the background information. So go down there to the Pi calculator that I've coded, download that, get it in your IDE. I'm going to be using Visual Studio Code. And then that's what the practical section is going to look like. Oh, this is the completed one. Okay. I have it there. Nice and easy. So I guess as you guys are setting stuff up, I can kind of maybe outline the files here. So we have our main file, obviously, is where we're going to start everything. We're going to go through the lexical analysis. We're going to go through the syntactical analysis, and then we're going to do the evaluation. We're not going to do a semantic analysis this time around, but I encourage you to give it a shot. And honestly, if you give it a shot, send it to me. I'm more than happy to look it over and give you praise for it. I think that would be a cool project. Okay, and then other things we have here. So we have our token class, Lex token. So I did leave this filled in. Just a couple notable things here. So we have a base class token, which is just going to keep the value. And then I've only defined two contextual tokens. We have a number token and a symbol token. And so obviously a number token is going to contain a number, and then a symbol token is going to contain a symbol. No need to touch that. And then these obviously are just going to print it out nice and easy so we can debug. And then other data structures we have are the AST nodes. So this is what the AST is going to be comprised of. So this is the base class here. And then we have a number, which is just going to represent a number. And then we're going to have the add operation, the subtract operation, the multiply operation, and the divide operation. So something to note here, there's only 3 functions per. So we have the initialize, obviously, function, or the constructor, which is going to take in a value for this one, and it's going to take in left and right nodes for these ones, right? Because it's a tree. And then at the end, we can actually fill in these evaluate. And the thing is, because this is a tree-like structure, in the add operation, which you'll see, you can actually call the left and right add operation. So it all evaluates really easy. Like it's super simple to set up. So definitely an advantage there. And so what we're going to touch is the Lexer file. So we're going to fill in this tokenizer function. And then we're also going to fill in all of the functions here. You can see we have some helper methods, and then we also have a function for each grammatical line as well. So yeah. Do we think we're good to start? Should we wait until a little bit longer, or is anyone not ready? You can just raise your hand if you're not ready, I suppose. If I don't see anything, I'll start. All right, so we can start. Now bear with me. I can kind of code in Python, but this is definitely not my first language. So that is a keep in mind. But I do have the code with me that I did beforehand, so that'll help me out. My main language is kind of just C++ right now. So, all right, so let's start off with our main class here. let's just make sure it's up and running. So we can do, print. You just start off with the hello world, make sure everything's working. Great, hello world. Hopefully everyone can see that. Nice and easy there. Cool. So we can start off with our input. So that's going to be the most important thing that we first need to evaluate. So let's just do a string here. Can be really anything, I suppose. Let's do, maybe 3 + 5 to kind of start it off easy. And so let's look at our lexer, because this is going to be the first stage of our pipeline here. So what's the lexer going to have? Well, we can just break it into one function because it's really not all that complex in this kind of scale. But one of the file, sorry. Cool. So first off the bat, we can see that it's going to return a list of tokens, right? So obviously the first thing we're going to do is just create an empty list of tokens like that. And then everything we're going to do from here is going to be inside of a while loop. So nice and simply, we're going to take our input, take the length of our input, and if it's bigger than 0, then we can keep parsing the statement, right? We just want to keep going through until there's nothing left. So we're going to have a string as the input, like we said, the 3 + 5, and we're just going to keep taking away characters from it and turning them into tokens until there's none left. It is kind of the approach we're going to taking. So as you can see here, if we're chipping away one per one, we're going to take our 3. And then what you'll notice is that there's actually a space here. So the first thing we want to do off the bat is strip the front of it. So what does stripping a string actually mean? Well, if you strip the front of it, it just means remove any white space. So if you have a string that's like this, it'll basically just turn it into that, right? So let's just take away the front part, nice and easy. Python, of course, has an easy command for that. Input.lstrip, right? Strip the left side like that. And then we're going to want to take the first character, right? So we're going to evaluate at the start of it and just keep doing our logic based on the first character. And that's going to be called a peek character. So we're going to be peeking forward. And why are we peeking? Well, we're peeking because we're going to be reading what that first character is, but we're not going to be modifying it. So if we were to consume the front character, we would take it, be able to use it, but it's going to be gone off the original input. So we're only going to be peeking because we're just going to use it here. Of course, the first index, nice and easy. And then we're just going to off the bat check if it's a symbol. So, a simple if statement's just going to work here. We can check if it's inside of this string, and we can just add all of our symbols in here like that. So, if, and remember, peek is going to be one letter, it's going to be a char. So if the character is a plus sign, if it's a negative sign, if it's a star, if it's a divide symbol, if it's a left parenthesis, if it's a right parenthesis, then this is going to run. And we're just going to add a token to the list. Or we can just, tokens.append. And what kind of token are we going to add? Well, if we can remember here, we're going to be adding in a number token, right? And that's just going to take a value of a string. Cool. We can do symbol token. And again, we're just going to feed it that peek character. Now, we've just taken that input and we've pushed it away to the symbol, but now we want to remove it from the start. So we can use some funky Python syntax here, which just removes the first character there and leaves the rest of the input. So this is just going to take away first character. Cool. And after we're done that, continue, and then we can start the process all over again. So that's gonna take away symbols, or it's going to parse symbols, sorry, lex symbols. And now we're going to start looking about numbers. Now, this is important for numbers. We can't just do an if statement, because here's the thing. If we just did an if statement, what would happen is we're just actually let's do an if statement. We can see what's going to happen here, because we'll cover all aspects of this as well. So let's just assume we do the same thing. So we can say .peek is digits, I think. Yeah, is digit. Okay, so if it's a number, then let's just add it, I suppose. We can do the exact same thing. Now, is this number? Okay, still needs a string, so we're all good. We're all good there. Okay, number token, and we can just, again, add the peek. Continue, but of course, we're going to be stripping away that first character as well. Cool. And then, so if it's not a symbol, if it's not a digit, then it's an unidentified character, and that's when we're going to throw an error. So we can just simply put in, simple just print statement. If we've reached here, then it means we've encountered. Right, so that's pretty basic, right? So we're just going through the input one character by character. Take the first letter, obviously remove the white space. If it's a symbol, add it to the symbol list. If it's a number, add it to the number list. All fine and dandy. And of course, after all said and done, we just want to return back the token array. And yeah, so that's actually going to work for our current input. So what we can do is we can move over here and we can do tokens equals tokenized expression. It's going to need the input, so we can just strip it off the bat. It might just be a good thing to do, and that's just going to take any white space off the end. I guess not really necessary, but kind of nice. And then we can just go for token in tokens, not recursively, but just print out every single token in the list, and that'll actually work. So if we run this, you can see we'll get the number token 3, the symbol token plus, and then the number token 5. Now, where I kind of mention that this isn't actually the proper way to do things is because there's a very obvious flaw in that, or maybe not obvious, but there's a very big flaw in this, and it's if we do 32, it's actually going to break that apart into two numbers. So we're going to get a 3, and then we're going to get a 2, and then we're going to get a plus, then a 5. So that's why I said there was a little bit of an error there. Also, Connor, if anyone raises their hand at any point, just let me know because I'm not looking at the stream. And then also goes for anyone. If anyone has any questions, just raise their hand as well or ask on the Q&A. Okay. So how do we fix this? Well, the answer is honestly just a while loop. It works pretty well in this case. So that's all fine. We can say that this, flex operators, I guess be symbols, but and then we can say that this part is just going to be, lex numbers. So what's a number going to have in it? Well, let's just start off with a string, and we're just going to add to the string. So we could say, another while loop while the input's still going strong, right? Well, there's still stuff in it, and the next character is a digit. Actually, we can just do peak. If peak is a digit, like that, right? So if we still have input and the next character is digit, just like our force, just like our if statement, let's just add to the number, just a simple string appendage like that. And then I guess, of course, we need to cut off the first character like that. Now, the last thing we need to do is update the peak, right? Because we just used it. So we can say that now the peak is going to be the new input of 0, right? Because we just trimmed it off. So this is going to be a new one. And then, yeah, so it's just going to keep going through until it no longer sees a digit. And then that's when it's going to break out. The last thing that's important here is we just want to say, if there is actually a number, right? So if it's empty, then there's no number, and we can say that nothing was found. But if there is a number, then we want to add it to the tokens. Right? Just like that. Okay. So now that we've implemented that, it'll all work just fine. So, I mean, hopefully. See, that's why I said hopefully. Okay, what did I go wrong here? So well length 0 and peak digit. Well, there. Let's go with the old school method that I had here and see if that fixes things. Does not fix things. Apologies, guys. Just trying to figure out what I did wrong here. So tokens, well, token 0 input, peak, beacon. Okay, number like 0 and 0. Oh, okay. Sorry. Here's what I did wrong. That was correct. That's fine. Sorry, if we find a number, we need to continue so that it doesn't error out. Oh. Okay. Okay, there we go. Okay. Okay. Sorry about that. Slight oversight. Yeah, we gotta be careful with these things. Sometimes when you work with these loops, there's little silly errors. Okay, so all said and done, I'll just go over it one more time. Or have a list of empty, tokens. Go through the entire input character by character. Take off the white space at the front. Get our peak input, which is going to be the first letter. If the first letter is a symbol, add it to the list as a symbol, and then take it away, and then continue is going to jump it right back up to the top so we can start the process again. For the lex number, again, because we're going to be parsing, or I guess lexing, multi-digit numbers, we're just going to want to keep appending them here in this while loop, and then this will break out as soon as we encounter no digit or the input's over. And then we just want to make sure that if there is actually a number there, right, because this could stay empty if this condition is false, let's add it in, and then we can continue, or else we'll have that error. And so that's our lexer there. Does anyone have any questions with the lexer? Apologize for that. Yeah, so we can see our program work here. Maybe we'll give it a couple more numbers. We can do, 32 plus 5, times 4, and that'll still work. It's good to test these things out, right? And, what if we add a semicolon at the end? Well, semicolon, we didn't define it. It's not part of our lexicon. See, it'll give us an error determining token for input, semicolon, right? Cool. Does anyone have any questions? Anyone pop their hand up if they have any questions? Okay, let's keep rolling. Cool. Next, we're going to be moving on to here, let's actually maybe do a little quick print statement just to make it a little bit cleaner. Okay, now we're going to move on to this syntactical analysis. Now, this is going to get a little bit more complicated because we're going to be working with their grammar, which is fine. So here we go. Let's just first go over the helper methods because these are going to make our lives so much easier. So, okay, so a couple common helper methods, and you'll also see this actually in more advanced lexers, like, for example, my programming language. The lexer, I know this is one function, but mine is like over 200 lines long. So they do get kind of more complicated as you scale up intensity. For this, it's, again, pretty good, but you'll be seeing kind of these if you ever read this sort of code. First is going to be the peak. So that's what we were saying. Now, something to acknowledge about this, what does the parser do? Well, we get our list of tokens, and we're going to be taking from the front. Now, there's two approaches you can take with this. Number one, you can just do what we did with the lexer, and just once we use a token, take it off the front, and then just have a new array. Approach number two is to keep an index of which token we're at. Now, there's an advantage. Well, there's actually not an advantage about. There's an advantage to one of them, and there's a severe disadvantage with the other one. So the easiest approach, or the most straightforward approach, is to just pull off the front, which is great. But if you know anything about data structures and algorithms, you know that arrays need to be resized after you remove it. So I'm not going to dive into complexities there, but if you take in the courses, removing from the front of the list is going to be an O(n) time. So we're not going to want to do that. Whereas we just increment an index, it's just going to be linear time, right? O of 1. So that's the method that we're going to take. It's going to make everything so much easier. Not that we're going for performance here, but it's always a good thing to consider. So what helper methods are we going to have here? Well, for our peak, like I said, we're going to be returning the token that we're currently on, but we're not going to be consuming it. What does consuming mean? That just means that we're going to be taking it away from the list, or, in our example, incrementing onto the next one. This is just a simple one-liner here. First, we have, well, we'll do it in 2 lines, I suppose. First, let's check our edge case, right? So, is there tokens? If there is tokens, right? If our index is less than the length of it, then we can just return the current index that we're on, right? So there you go. That'll return if there's the space for it, then let's return the one that we're on. Otherwise, this should happen. we'll just return none. And that's basically just means that, we're at the end of the list. There's no next token, right? So nice and simple there. What does consume look like? Well, consume is going to be the exact same thing, except after we return it, or sorry, I guess before we return it, we're just going to take it off, or in this case, increment our pointer. So we're going to store the token. That's next, which is just we can just make use of our peak function. And then after that, let's just, increment the index by 1, and then simply remove the token like that, nice and simple. Okay. Expect. Now this is going to be when we're matching our syntax. So the objective of this is to make sure that let's take our current token and see if it matches with the token type and the value. And so sometimes we just want to match by the type, like we want to say, is this a symbol? Is this a number? And that's enough. So that's why we provide this kind of already predetermined value. But maybe sometimes we want to say, is this a symbol and is it a parenthesis? So those are kind of two different edge cases. Well, not edge case, but those are two different cases, and we can just use one function to represent that, which is fine. And so because we're using base classes and polymorphism, then we can just do is instance. And so there's this nice Python command. It's instance of in Java, if you're familiar with that. And so we're just saying, is the token we're on right now token type, right? So if we put in token type, let's say, I don't know, symbol token, we can say, well, is the current token we're on a symbol? And then if there is a value, we'll have to if there is a value, we'll have to check that as well. You can say is, if there's a value, instance, and if the next character is equal to the value, right? So let's just check, if there's a value, let's make sure that's also all good. Otherwise, we can just return is instance, and that'll be enough of a check for us. Okay. And so that's kind of our helper methods that we're going to need, and we're going to be using those exclusively. Everyone good with the helper methods? Does this make sense? It'll make a little bit more sense when we actually start using them. Okay. So we can really start anywhere here. And this is going to be called top-down parsing, and it's recursive in nature, in the sense that we're going to be calling all of these functions multiple times inside of all of them. So, let's read back to our grammar. For example, an expression here, if we want to get the term, we just call build term. If we want to get the factor, we just build called factor, right? If we want to get the expression, we just build the AST again, right? So we're only going to be focusing on each individual section, and they'll all nicely kind of compile together. So let's start with the most basic one, I suppose. Let's start with our build AST. So this can be a root function here. So this is just going to be building. Let's look at our grammar. So what is an AST? Well, it's just an expression. That's really easy. So we should say that our expression is going to be, build expression, right? No need to add any more to that. We already have a function for that. Let's just use that. And then as kind of a nice thing too, think about it. By the end of this, we'll have used our entire token list. If not, then we have a bunch of useless tokens. And so that's kind of an error on its own, right? So if there's a new, after we get to the end of the list, and we look at the next token, if it's not, none, right? So if there's tokens left over after we've assembled everything we need to assemble, we can just, raise an error there, which is fine. But that's not going to happen if we do everything correctly. It's just kind of a sanity check for ourselves. And then let's just return the expression there. Okay, boom, nice and simple. That's our first parsing method completed. And so, I don't know, we can start with any other one. This one's kind of nice and easy. So what's a factor? Well, factor is either going to be a number or it's going to be an expression with, parentheses around it. So let's see how this is built. All right, so, okay, here we go. So build factor. So there's, two possible outcomes for this. Either it can be a number either the first thing we find is a number or the first thing we find is going to be that symbol. So let's start off with a number. If is instance, actually we can pull in our expect here, right? Self. Right, so we're expecting, a number here. Okay, so take our first input, right? This is the first thing on our token list. and we want to make sure, is this actually a number? And if it is, great, let's get the value of that. We can just, pass it to an int and consume that character. Make sure to consume it so we don't just use it and then leave it in the stream. That'll lead to a whole bunch of errors. And then, right, there's nothing after that. It's just number. So we can just straight up return that. And keep in mind here, we're returning an AST node. So let's go look into our AST nodes and see what would be the most appropriate thing to return. In this case, it's just going to be a number, right? So let's just return a number. Sorry. AST nodes dot number. And just throw the value in there, right? So that's super simple. Self.expect. So yeah, if it's a number, let's just check if it's a number token. If it is, grab the value and then give back the AST representation of that. Okay. Well, what if it's not a number? And in that case, we're going to be looking for this. Okay. So naturally, what's the next thing we're going to want to do? We're going to want to check if it's a open parenthesis. So I code in a little bit of a silly way. I got to be honest. I like to check the worst case first, so that my entire code isn't just in all of these different if statements. So let's first check the case of, what if we don't have an open parenthesis starting off? Well, if we don't have an open parenthesis off, we know it's not a number. In that case, it's invalid. So let's just get that check out of the way. If we're expecting at least a symbol, and the symbol is going to have the value. It's going to have the value of an open bracket like that. And if it doesn't, we're just going to have to raise a syntax error that we expected an opening bracket in our code, which is fine. And then that'll, because we raise it, that'll end the program there. So now it's fair to assume that we know the first token, it is going to be a open parenthesis, but keep in mind, we need to consume it. Make sure to consume it, right? We don't want to just keep it there wandering around. Cool. Comment here, consume the. Okay. All right. What's the next thing? So we've just taken the first part of this out. Cool. And now we need an expression. Like I said before, make use of your recursive functions. We can just literally say self.expression. Nice. And then again, we're basically doing the exact same thing. Check for that closed parentheses. Just reverse this. We want that closing parentheses there. Consume it. And if we've made it to this part, we can say that this is valid. So we can return the AST, which is just going to be the expression. Now, why is it just the expression? Because remember what I said, we're omitting that, redundant syntax, right? When we're constructing these trees, it doesn't matter that there's parentheses there. The reason that the parentheses are there is to express grouping and order of operations. And since our grammar already considers that, we don't actually need it. All we need is the expression. So that's just what we're going to return there. Cool. And so now we have only two more to add. So they're pretty much the exact same thing. So let's just start with, I guess, build expression here. So this is going to be for your plus and negative ones. And same sort of deal here. So we're always going to start off with a term. Okay. And if we don't have a term, it's not valid. So start off with a term. This is going to be the left side of the operation, right? Because if we do, number plus number, the first term, that's going to be the left side. So again, build, what are we looking for? We're looking for a term, build a term. And then if there's nothing after that, right? Because look here, so this is actually a star, which means that this entire part doesn't need to be there. We can just return a term, that's all fine. So in that case, if there's nothing after that, if term's the last thing, then all right, we can just return that left side. Okay. Otherwise, what do we need now? Well, we need to make sure that there's either a plus symbol or there's a negative symbol. That's the next thing we need to cover. So again, sort of same deal. If we'll break this up here. If the expect, so Okay, if it's a symbol token, yeah. Sorry. I'm throwing myself off here. Oh, I'm so sorry. Python syntax threw me off. I forgot what our expect. So our expect method actually doesn't take an input because we actually peek inside of this. So that's my bad. Okay, so for the expect ones here, we just need to pass if it's a number token, that's fine. For the this is done correctly. This is done correct. Okay, so it was just the one place I messed up. Okay, my apologies, guys. Okay, sorry. Okay, I was a little bit confused there. So okay, so if the next one's a symbol token, we want to make sure that's a plus sign, right? Or a negative sign, correction sign. Okay, and if that's the case, then we can get our operator, because that's going to be our next one. Right. And we got to make sure it's the value, because if we just consume it, that's going to give us the token. We're actually looking for the symbol specifically. That's the operator we're using. And then we're going to get the right side, which is going to be just the build term. All right, so now we have the operator, and then now we have the token. So we have the left side, we have what we're doing, and then we have the operator on the right side, or sorry, the expression on the right side. So what are we returning here? Well, we're either going to be returning an add operation or a subtract operation. And I mean, that's just a simple, if statement or like a case statement. I don't know. You can use a switch statement here. That's what I would probably do. Well, that's what I did do, right? Match the operator. If it's a plus symbol, then you can just return, add, what did I do? AST nodes, add. Same thing. Oops. Subtracts. Okay. And then the reason I like to do this is just because if there's anything else, which again there really should not be, but it doesn't hurt to make extra checks in these sort of situations, just for your own sanity. Believe me, it helps in bigger applications. And then yeah, so that's pretty much it. And then that'll cover it. One thing I will say, just we're going to build this out first, but what I didn't consider was chaining operations, right? You see there's a star here. What does that mean? Well, it means none or more. And so this is just an if statement. So this is only going to count for one extra chain. If we wanted this to be repetitive, we're going to need to put a while loop in here. But let's just put this in for now. We'll get it running, and then we'll throw a while loop in after. And now we can literally copy this, paste it, because it's the exact same thing. Except this time, we're just going to be looking for the multiplication, and then we're going to be looking for the division. And then, of course, instead of building terms, we're going to be building factors. Like that. Factor. And then, of course, so these, we're going to be doing our multiplication and division. Like that. And yeah, I mean, that's literally it. So that is it completely built up. And hopefully that was all correct. We can actually give it a go. Like I said, we can't chain these operations here right now. So we'll just kind of run it like that. Let's do, we can do AST equals parser build AST. How did I set this up? Sorry, my Python knowledge is not great. AST equals parser. And I threw in tokens, build AST. Okay, and then we're going to print that AST out. So by this point, hopefully we should get exactly what we're looking for. Cool. Oh, not cool. Interesting. Okay, so it looks like here that it is correct. We do have an add operation, but it's looking like we have a none, which is a little bit odd. So we know that this is going to be, I guess it's always good to go over like debugging, right? Like you're never going to get these applications perfect. I do want to stress that. I did pre-code this. I'm going a little bit off script here, but in these kind of complex systems, you're never going to get these perfect. They're kind of really finicky to start off with. But I could show you how we break it down here. So this was an add operation. And that's what it messed up here. So we're going to be looking at this specifically. So why would this have been none? Well, the left side is none. So I'm seeing that build term is where we're going wrong. And now why is build term going wrong? So we get the factor. And so build the factor. Double check code here. Oops. Expect a number token. If not, there wasn't an error. Okay. So I'm thinking that this is going to be giving us the error here. So we'll do a quick print. We'll say I think that's where it's going to be giving us the error there. Oh, can you not? How do you concatenate stuff in Python? Is it that? Oh, what am I saying here? Oh, sorry. Expression. We got the left side. Okay, so that's not null, which is odd. Oh wait, that just prints value? I'm so sorry. Print. I don't encourage it, but for the sake of time. Okay. Well, it seems like I kind of shot myself in the foot a little bit by trying to go off script. So I guess we can just go back for the sake of time. I know it's getting a little bit late, guys. I apologize. Let's just go into like, I guess originally what we were going to do anyways. So instead of turning this into like an if statement, let's just turn it into a while loop here. So like I said, we're going to be constantly wanting to break these expressions into, as many as we can. So we're going to be wanting to go, expect, we keep finding these symbols here, right? Because they start us off, then we're going to want to build up the operator. It's pretty much the exact same code, just in a while statement. That's the operator. It's fine. But here's the difference, and I think where we got caught up is that because this is recursive, when we're adding and chaining on operations, we're not just returning. What we're actually doing is just setting the left side to a different operation. And this is going to recursively pull operation chaining together. So if we're adding on, multiplication of factor or division to a factor, we're just going to be setting the left side, which will open up the right side for another node. And then after that, when that's all said and done, return the left side there. That should be good, hopefully. Looks good to me. Make sure that it is. Okay. And then we can just take that and then put it on the right-hand side. And then, of course, we're replacing these. So for build factor, we're going to want terms. Term. Session term. Okay. Plus minus. And then my own sanity check. Oh, shoot. The one last thing that I forgot to do was for these, it's not going to be multiply, it's going to be add and subtract. Okay. Sorry about that. Okay, so now that should be the completed code. If we do run that now, there we go. So as you can see, we take the number 32, we add the number 5, and then this will also add in, order of operations, hopefully. So we can see this 32 plus 5 times 2. What you want to see is that this is lower in the hierarchy because we want to evaluate it first. So as you can see, we want to add the number 32 and the result of the multiplication of 5 and 2. So as you can see there, that all works. But if I was to do, obviously this, group these together and then multiply the sum of that after by 2, that'll also work. So you can see how that kind of all got switched around like that, which I think is super, super neat. And so that was what I was saying about the power of grammar, is that we didn't have to add any logic to manually reshuffle these expressions around. We didn't have to do anything. Well, I mean, we had to do something, but we didn't have to add any additional logic to break our system. And this will fully work. And the last step, which is the quickest step, is to actually evaluate. And this is shockingly easy. We're going to go into our Lex tokens here, and we're just going to fill in the evaluate stage. Oh, sorry, not these. The AST nodes, evaluate stage. So for this, for a number, we're just going to return the value. Nice and simple. For add, we're going to return the left evaluate plus the right evaluate. You probably see a trend here. Subtract. Multiply. Divide. And that's literally it. Hopefully. And then at the end of that, we can just do print ast.evaluate like that. And so let's try something here. We can do 14, times 2, or say 13 maybe or plus 6. So that's going to be 20 times 2 is going to be 40. And there we go. We got the result 40. So that's the full calculator. Yeah, so there we go. We got there eventually. So yeah, thank you so much. If anyone has any questions, let me know. I don't want to keep you guys for too long. It's 8:30. So last chance for questions, I suppose. All right. Well, Connor, what are we saying?
We just got a comment from Pushback. They liked the event. Pretty cool in their words. Cool. So yeah, we're great to see everyone this evening. Have any questions, feel free to reach out to the team. As we're building out our next events, always looking for new participation. And also, as we build out one of our new teams, we'll be looking for a few people if they'd like to help us out. We'll be putting the applications up soon, and then just start through our interview process.
And then if anyone wants, follow-up questions or whatever, they can join our Discord, and you'll see me. I'm the hackathon lead in there. Just message me on Discord if you have any questions, or LinkedIn or whatever. And I'm very happy to help anyone else out that needs any help. Or if you're even curious about, hey, how do we go from this to a programming language? Also happy to explain that as well. So yeah, thank you so much, guys. This was really special for me. This was, I guess, our first workshop to kick off the year. So hopefully we'll be able to do some of these. Well, we will be doing some of these in person. Hopefully we'll be able to see some of you guys there. And yeah, keep an eye out for the hackathon positions if you're interested. Love to have you guys on the team.
Yep. Yeah. Okay. Thanks so much, everyone, for attending, and feel free to reach out on LinkedIn or however you want to connect.
Oh, sorry,
guys.
William. There's just one more question.
Yeah, what's up?
Oh, we got one more.
Okay.
Go ahead. Oh, I see. Okay, Brian is asking, why did we have separate functions for add, subtract with a build expr inside the brackets versus multiply/divide and using a build term instead?
Yeah. So the reason that we handle the operation separately is purely back to the idea of order precedence, right? Because in BEDMAS or PEGMAS, depending on how you do it, you know that multiplication and division are they take precedence over add and subtraction, right? So I mean, I don't really have to hopefully explain it. It's 5, type fire. We want to evaluate this expression first before we add 2 to it. So I'm not going to go into depth of like how the grammar works. I know it's a little bit confusing, but the way that we express that sort of stuff is by breaking them up into the same thing, right? So if we just had one expression for all operations, then that would be essentially saying that they all have the same precedence, which is just not true. So this allows us to execute multiplication and division first before we use our add and subtraction. So that's where you'll see it. I know it doesn't really make all that much sense at a surface level view of why we would separate that, but it's purely because that's what actually enforces the order precedence that we see. Oh, there's the thank you slide. There you go, guys. Thank you. All right, sweet. Anyone else too? You can also turn on your microphones. I think Connor still had that as well.
I'll turn it up. Yeah, so you can unmute your mics if you'd like. And yeah, perfect. We hope to see you at our next few events, and check out your emails. You should be getting a post-event survey. We love to get that feedback, so we can identify what you're looking for in our next events, and also so I can get more budget from Google to support events in our communities as well. So the more active engagement they see, the more they're willing to give us more budgets. So helps you, helps us. Okay. We will end it there. Thanks so much, everyone.
Thanks so much, guys.
Thanks, William.
Hello.